Today we are going to do the experiment on free convection overheated horizontal cylinder. So as usual, write down the course code, write down your name and ID, lab section, experiment number. So this is experiment number 4. Title of the experiment, free convection overheated horizontal cylinder. So write down the date, report submission, and now we'll come to the objective of the experiment and the experiment. So first I will explain the equipment description and then we'll go to the objective.
So we have a lot of examples, or we can take free convection from the pins. We can choose free convection from pins, or we can choose, there are a lot of configuration we have, but we choose a single rod. The rod is like this, and this rod is connected to the heater, and there is a one thermocouple. We can measure the temperature of the metal, the surface temperature of this metal rod. Okay, so when this metal rod becomes hot, the heat will be transferred, and the air here will become hot, and here the air is cold, and the cold air, it is a heavy air, it will push the hot air out. So we need to keep this open so that cold air, so we need to turn it so that the air will go naturally. So there is a fan, so we are not going to operate the fan. Next week we are going to operate the fan for forced convection. So today is a free convection, and we need to first step make sure this is open so that a outside air will go inside, and this hot air will go outside. Because of density difference, the air will start flowing over this cylinder naturally. Okay, so here we can measure the velocity, but for natural convection no need of velocity. So here we need to measure the surface temperature of the rod by using this thermocouple, and this thermocouple is connected to 10, because here I can't connect it, so we need to connect it to 10 because of the big socket. And there is another thermocouple which is here, which will measure the atmospheric temperature, and this thermocouple is connected to 9, so I need to measure T9 and T10. Okay, then I need to measure the voltage and current, how much voltage and current is given to this heater, so that I can find heat, so this heat will flow outside. So first steps, make sure the throttle wall, it is called throttle wall, or it is called inlet wall, whatever you easy to remember, you can remember it. So open this inlet wall so that naturally air will go inside. Then make sure the back switches are on, and then main switch on. Keep it on voltage and adjust the voltage to give on 5, 7. Okay, so first I will make it 5, and then 7, then 9. So increase this voltage to 5. It on T10, T8, T9, T10. So it is start heating now. So we'll wait for steady state to reach, and then we'll record the temperature and current. After steady state, after 20 minutes, we'll adjust this voltage to 7 volt, and we will wait for 20 minutes and we'll record the
Equipment consists of a horizontal cylinder. This is a horizontal cylinder. On other side of the one end of the cylinder is having heater. So there is a heater here, electric heater here, and this horizontal cylinder is heated by using this electrical coil through which voltage and current is flowing, so I can find out the amount of heat flow. So this cylinder will become hot. If you see from the side, it will look a circle, and which the diameter D is given to you as D is equal to 0.01 meter, and the length of cylinder is 0.07 meter. So this is diameter D is equal to 0.01. So this is capital D, and this is length L. So this is length L. So this cylinder is enclosed in a tailpipe which is having open end. So like this. So this is a open end. There is a thermocouple here which will give you the atmospheric temperature TA, and there is a one thermocouple here which will give you the surface temperature TH. This is about the experimental setup. This rod is hot, so due to the natural, there is no air flow. Heat will be transferred in upward direction because of the gravity, like in upward direction from the downward direction. So same amount of heat Q will flow like this because of the density. So according to Newton's law of cooling, the amount of heat flow from hot surface is proportional to area of heat flow area into temperature difference, delta Th minus delta Ta, temperature of surface. So this temperature is Th and atmospheric temperature is T. So here if you remove the proportionality constant is replaced by H and A Th minus Ta. So here our objective is to find out the H. So what is H? H is the heat transfer coefficient for free convection and it is defined as H is equal to Q by A delta Th minus Ta. So the unit of this is given as Q is in watt, area is in meter square and temperature is in degree centigrade. So watt per meter square degree centigrade is the unit of heat transfer coefficient. So today we are going to find out that. So this we are going to find by experiment, EXP. So it is called experimental and theoretically also. If you study a free convection, so what we need to study, we need to find out what is the temperature of heated surface, what is the outside temperature, atmospheric temperature. So we can find out, and we need to find out the area. So this area is very important, heat transferring area. Now in our experiment we are considering the circular, horizontal, cylindrical bar. So a natural convection will take place which is at Th temperature and outside is Ta. So heat will be transferred in all directions. The air near about bar will become hot and here the air is cold air. So this air will be a hot air and due to the density difference the hot air will go and cold air will push the hot air, cold air will move the up and hot air will go outside through this pipe. So now how the heat will be flow? So heat will be flow like this. So there will be a boundary layer separation. So this distance will go on increasing. So this is called a boundary layer. So here the heat will be transferred like this. Now we need to consider the heat transfer various numbers which are involved in free convection. So first number, the free convection, the non-dimensional numbers involved, number one is a Grashof number. So it is denoted by Gr and it is given by G because of gravity, natural convection, G beta. What is beta? I will explain it. Beta rho square and D cube Th minus Ta divided by mu square, where G is a gravity, B is a thermal coefficient of expansion, rho is a density, D is the diameter. Now in sometimes we need to replace this D by L, D or L. So what I should choose, how I can choose, what is the dimension for that? Whether D is correct or L, it is very important. D or L. So we can replace this formula as L also. Somewhere I can write this formula also. Grashof number is equal to G beta. I can take this rho square down. Mu by rho is nu, kinematic viscosity. So D or L cube, I can write L cube, Th minus Ta and nu square, kinematic viscosity. This is a dynamic viscosity, this is kinematic viscosity. Now, here the confusion. Why to choose L, why to choose D? And now in this week we are going to study a horizontal cylinder. Next week we are going to study a vertical flat plate. In vertical flat plate, heat will be transferred like this, and like this. So this is a boundary layer separation. And here we need to choose this height, this dimension for the Grashof number, L. Okay, now here the effective length, here the heat transferring length is this much and this is equivalent to diameter. That's why we need to choose diameter. Next week we are going to choose L. Why? Because of the flat plate. So first important formula out of that, the Grashof number. So following numbers, that is a Grashof number. So I'm going to write here Grashof number is equal to G beta D cube TH minus TA divided by nu square. Now all this where G is gravity, it is in meter per second square. Beta is thermal coefficient of expansion, unit is per Kelvin. Then D is the effective length and it is in meter. Then temperature TH is in degree centigrade and kinematic viscosity, it is in meter square per second. So if you put all the unit, it has no unit. That's why it is called a dimensionless number. So sometimes this formula G beta rho square D cube over mu square, or I can use mu by rho. It depends on the table what is given to you. Sometimes I have the table, the last page. Yes, kinematic viscosity is given, thermal conductivity, Prandtl number, rho, and T. So another number, Prandtl number. Why it is in table, I will explain. Prandtl number, it is denoted by PR and it is given by mu Cp by K. Dynamic viscosity, specific heat, and thermal conductivity all are properties. That's why it is a property. And in the table it is given as a Prandtl number. It has no unit as a like dimension number. Sometimes this table is not given like this. Sometimes table will be given in different way, like in manual. See here, temperature is given in degree centigrade. Density, specific heat, mu Cp. Mu is not given. Kg meter per second, yeah, this is mu. So I will write because of symbol. So this is a density. This is a density kg per meter cube. This is a specific heat, and this is watt meter Kelvin, means it is a thermal conductivity K. Then this is kg meter per second, means mu dynamic viscosity. This is a meter square per second, means it is a nu, and this is a Prandtl number. So Prandtl number is mu Cp by K. Okay. And here we can use the formula, rho is given, Cp is given. So Prandtl number, sometimes the Prandtl number is not given. So Prandtl number is not given. So no need. We can calculate from here. Mu Cp by K. So this into this divided by this, you will get this. Okay. So this is a column created in Excel. It is not necessarily it should be given. We will come back to this. The Grashof number first. Second Prandtl number, and then number 3 is a Nusselt number. So it is denoted by Nu and it is given by Hd by K. So here, sorry, again I will use the capital D, Hd by K. Here it is a heat transfer coefficient. It is by using these numbers and correlations formulas, so that H is called empirical or theoretical. And whatever we got by the Newton's law of cooling, that is a experimental. So we need to compare these two. And this K is a thermal conductivity and this is a diameter. And these three numbers are related with the correlation, and that correlation is given to you or it is available in the data heat transfer data book. So these correlations, there are so many correlations, depends on the application, this relation changes. So that's why it is given. So for horizontal cylinder, the Nusselt number is related with, is given by C. C is some constant into RA. RA is a Rayleigh number, and that I will explain it. What is Rayleigh number? Raised to N. So C and N is taken from the table, another table. So this table is given to you again. Yes, from this C and N is taken from this table. Now depends on the condition. I will show you what is the condition. So we need to find a Rayleigh number, and in that we need to choose. Where a Rayleigh number is nothing but product of two numbers, Grashof number and Prandtl number, Rayleigh number. Now we'll write the objectives of the experiment. Number 1, to determine heat transfer coefficient from hot horizontal cylinder. Number 2, to compare heat transfer coefficient obtained experimentally and empirically by using formulas and equations. And number 3, to understand Newton's law of cooling. So these are the objectives and experimental setup I explain here. And now procedure, see the procedure and write step by step. Number point 1, point 2, point 3. See the video carefully and write. It is very easy. Now result and discussion. So here in observation we need to write what is the given to you. Whatever the things given to you. Observation, the diameter of the horizontal cylinder D is equal to 0.01 meter. Number 2, length of cylinder is equal to L is equal to 0.07 meter. And number 3, property table as given here, property table and heat transfer data book. It is not given, it is just I attached at the end of the report, but it is available, heat transfer data book for further study. Now in observation table, I told you it is given directly, but what is the observation? We are going to measure the voltage V, we are recording current, and we can calculate Q. So this is a calculation part. We are measuring TH and T8. So from the equipment, we can measure this as T10 and this is T9. Okay, and then this is a calculation part. So we'll come back to this. We'll record the readings from the experiment.
And now for 5 volt, write the current 0.77 and TH equal to T10 84 and TA equal T9 20.9.
For 7 volt, record the readings.
1.05.
And T10, that is TH. T10 is TH, remember, 124, and T9 is TA, yes, T9.
20.9.
Keep this voltage on T10 and temperature on T10 and reduce the voltage to 0. So make it 0 voltage. Make the 0 voltage and switch off.
For experimentation, we will record the readings and we will write here. At 7 volt, current is 1.05 ampere. So this is a volt, this is ampere, and this is calculation. And we record the temperature T10, 129 degrees centigrade, and it is nothing but a T10, remember, from the machine. And it is a heater surface temperature or heater temperature, and this is degree centigrade, which is recorded from machine T9, and it is 20.9. And the second reading at 5 volt, the current is 0.77. This we'll calculate it, and the temperature T10 is 84 degrees centigrade, and 20.9 atmospheric temperature is 20.9. Now we'll come back to the calculation part. So only 2 readings, no need of these readings, only 2 is enough. Now we'll move to the sample calculation. The sample calculations are little lengthy, so one by one we need to make. Number 1, heat flow is equal to Q is equal to voltage into current, and it is, I will do for the second reading and you can do at home for first reading. My aim is experimental. By Newton's law, Q is equal to HA delta TH minus TA. Okay, so now I know Q. I need to find the area. So which area I need to select? Number 2, heat transferring area. Heat transfer area. It is very important to get the area. What is the formula? It is a horizontal cylinder. So student, make here pi by 4 d square. No, last time we took this. This is not correct. Okay, so which area, heat transferring area, it is very important. Now I will go back to the experiment, and here I explain. This is a horizontal cylinder. If you see from side, like it is a diameter D, so heat is transferring from the length and this periphery. So along this length, and this is diameter D. So this is a circular. So here the area is pi d, means this length, like a pi d perimeter. If I open this, it will become a rectangle pi d, and it's a length L, pi d L. Okay, so this area is very important. Now I'll keep this here, and the area is pi into 0.01 into 0.07, and is equal to 2.199 into 10 to the power minus 3 meter square. And now I know Q, I know a temperature is there, so I can find out heat transfer coefficient by Newton's law of cooling, and it is written by H is equal to Q by A TH minus TA. 0.919 watt per meter square degree centigrade. So this is by experimental method. That's why it is called EXP, experimental. Now we will move to the empirical EH, how I can calculate. So first I need to find out the properties of air is taken at average temperature, is taken at average temperature from given table. T average is equal to TH average. Average means plus TH plus TA over 2. 74.95 degrees centigrade, and it will be plus 273, 347.95 Kelvin. Now I will go to the table, and 43. So here, in between these two, so I will choose this. You can take the interpolation or directly, because 53 and 47, it is very near to each other. So you can take this value as it is. Better way to go for interpolation. Use the interpolation formula and write the values. Now I will not do the interpolation. We will write, your result will not be changed. So here we will write density is 1, Prandtl number 0.07. The density of the air is 1 kilogram per meter cube. Then Prandtl number 0.708 is equal to mu Cp by K, as I explained before. If this is not given by this formula, we can calculate. Then thermal conductivity of air is 0.0299 watt per meter Kelvin. And then kinematic viscosity is given, nu is given 20.94 into 10 to the power minus 6. Don't forget this value. Student forget in exam, meter square per second. So these are the property given. We'll find the numbers. As I told you, I will find all the numbers. For this Grashof number, I need beta. G is known to me. I need beta, and I have all properties. So number 5, thermal coefficient of expansion is called beta, and it is 1 over T average. The temperature should be in Kelvin, must be in Kelvin, because it is in multiplication and division, it should be in Kelvin. 347.95. So your answer will be 2.873 into 10 to the power minus 3 per Kelvin. So once we know the thermal conductivity, I can find out the Grashof number. So number 6, Grashof number for heated horizontal cylinder is given by Grashof number is equal to G beta T cube TH minus TA divided by nu square. Okay, so why I choose D here, I explained before. If this is a circle, so heat will transfer like this, heat flow will be like this, and this is a boundary layer separation. So you need to take this effective length, and which is a diameter of cylinder. So here D. If it is a plate, we need to choose that vertical length. Now Grashof number we can find out. So GR is equal to G beta D cube TH minus TA divided by nu square. G is 9.81 into beta is 2.873 into 10 to the power minus 3 into 0.01 cube
into pH 129 minus 20.9 divided by kinematic viscosity 20.94 into 10 to the power minus 6 whole square.
6948.274. So 7 done. Now 8. Rayleigh number is equal to RA is equal to Grashof number into Prandtl number. 4919.378. Nusselt number is given by correlation or empirical relation as Nusselt number is equal to C Rayleigh number raised to n, where C and n is taken from the graph or from the table for RA. So we will go to the table and the table is given to you. So what is your Rayleigh number? Rayleigh number is, so this is near about 100 to 10,000. This is 0.01 to 100, 100 to 10,000, 10,000 to 10 million. And now our number is here 4,919, near about 5,000 our number is. So we need to choose C and N. This from given table, C is equal to 0.085 and N is equal to 0.188. So Nusselt number is equal to 0.85. Rayleigh number raised to 0.188. But Nusselt number is equal to HD by K. So this H is a empirical because we are using formulas. That's why empirical. And this Nusselt number I will equate to above equation 0.85. Rayleigh number raised to 0.188. Now I have everything. I will put the values. I don't know yet empirical diameter. So capital diameter 0.01. Thermal conductivity of air is 0.0299 is equal to 0.85. Rayleigh number is 4919.378 raised to 0.188. Solve this equation and we will get H empirical is equal to 12.56 watt per meter square degree centigrade. Transfer this value in the calculation table. So Grashof number, experimental and empirical. So experimental value is 30.919. Heat is 7.35 watt. Experimental 30.919 and Grashof number 6948.274. Experimental 12.5651. Similarly calculate these values and write your answer here. No need to write the sample calculation for other reading. Now conclusion. Write from the objective. What is conclusion? Number 1. The heat transfer coefficient obtained experimentally at HEXP and HEMP 30.919 and 12.565 watt per meter square degree centigrade. The H heat transfer, H experimental is around twice H empirical.